Welcome to episode 14 of our AI series, where we will delve into advanced machine learning techniques that can significantly boost the performance of your models. We will cover ensemble methods such as boosting, bagging, and random forests, time series analysis and forecasting, advanced optimization techniques, and anomaly detection. Each topic will be explained in detail, followed by hands-on projects to help you solidify your understanding. Remember to like, subscribe, and turn on notifications so you don't miss any future episodes. 1. Ensemble methods: boosting, bagging, random forests. Boosting. Boosting is a technique that combines multiple weak learners to create a strong learner. It focuses on training models sequentially, with each new model correcting the errors of the previous ones. The goal is to reduce bias and variance, improving the model's performance on both training and unseen data. Detailed explanation. 1. Step 1. Initialize by training a base model, e.g., a decision tree, on the entire dataset. 2. Step 2. Evaluate the model and identify the instances it predicted incorrectly. 3. Step 3. Increase the weight of the incorrectly predicted instances to make them more important for the next model. 4. Step 4. Train a new model on the updated dataset with adjusted weights. 5. Step 5. Repeat the process for a specified number of iterations or until the errors are minimized. 6. Step 6. Combine the predictions of all models through weighted voting, classification, or averaging, regression. Code example. Explanation of code. 1. Data generation. We use make_classification to create synthetic data with 1000 samples and 20 features, which helps in demonstrating the model without needing a real dataset. 2. Data splitting. The data is split into training and testing sets using train_test_split to evaluate the model's performance on unseen data. 3. Base model initialization. A simple decision tree classifier with a maximum depth of 1 is initialized as the base model, which will be boosted. 4. AdaBoost model initialization. We create an AdaBoost classifier, specifying the base model, the number of estimators, 50, and the learning rate, 1.0. 5. Model training. The boosting model is trained on the training data. 6. Making predictions. Predictions are made on the test data. 7. Model evaluation. The accuracy of the model is calculated and printed. Bagging. Bagging, or bootstrap aggregating, involves training multiple models on different random subsets of the training data and then combining their predictions. This approach helps reduce overfitting and improve the model's stability and accuracy. Detailed explanation. 1. Step 1. Generate multiple subsets of the original dataset by sampling with replacement, bootstrapping. 2. Step 2. Train a model on each subset independently. 3. Step 3. Combine the predictions of all models through majority voting, classification, or averaging, regression. 4. Step 4. The final prediction is more robust and less prone to overfitting. Code example. Explanation of code. 1. Base model initialization. A decision tree classifier is used as the base model for bagging. 2. Bagging model initialization. We create a bagging classifier, specifying the base model and the number of estimators, 50. 3. Model training. The bagging model is trained on the training data. 4. Making predictions. Predictions are made on the test data. 5. Model evaluation. The accuracy of the model is calculated and printed. Random forests. Random forests extend the concept of bagging by adding another layer of randomness. Instead of using all the features for each decision tree, a random subset of features is chosen, making the trees more diverse and the model more robust. Detailed explanation. 1. Step 1. Generate multiple subsets of the original dataset by sampling with replacement. 2. Step 2. For each subset, train a decision tree on a random subset of features. 3. Step 3. Combine the predictions of all trees through majority voting, classification, or averaging, regression. 4. Step 4. The final model benefits from reduced variance and improved performance. Code example. Explanation of code. 1. Model initialization. A random forest classifier is initialized with 100 trees. 2. Model training. The random forest model is trained on the training data. 3. Making predictions. Predictions are made on the test data. 4. Model evaluation. The accuracy of the model is calculated and printed. 2. Time series analysis and forecasting. Introduction to time series analysis. Time series analysis involves analyzing data points collected or recorded at specific time intervals to identify patterns, trends, and seasonal variations. This type of analysis is crucial for making informed predictions about future data points. Key concepts. 1. Trend. The overall direction or movement in the data over time. 2. Seasonality. Regular and predictable patterns that repeat over a fixed period. 3. Noise. Random variations that do not follow any specific pattern. Time series forecasting. Forecasting involves predicting future values based on historical data. Techniques such as moving averages, exponential smoothing, and ARIMA models are commonly used for this purpose. Code example. Explanation of code. 1. Data generation. We generate synthetic time series data using NP, random, RANDN, and CumSum, which simulates random walk behavior. 2. Data visualization. We plot the generated time series data to visualize its trend and pattern. 3. Model fitting. We fit an ARIMA model to the data using the ARIMA class from the stats models library, specifying the order of the model as 5, 1, 0. 4. Making predictions. We use the fitted model to forecast the next 10 time steps. 5. Plotting predictions. We plot the original data and the forecasted data to visualize the model's predictions. 3. Advanced optimization techniques. Introduction to optimization techniques. Optimization techniques are used to find the best parameters for a machine learning model, minimizing the loss function or maximizing the accuracy. Advanced techniques include gradient descent, genetic algorithms, and Bayesian optimization. Gradient descent. Gradient descent is an iterative optimization algorithm used to minimize the loss function in machine learning models. It involves updating the model parameters in the opposite direction of the gradient of the loss function. Detailed explanation. 1. Step 1. Initialize the parameters randomly. 2. Step 2. Compute the gradient of the loss function with respect to the parameters. 3. Step 3. Update the parameters by subtracting a fraction of the gradient, learning rate. 4. Step 4. Repeat the process until convergence, when the parameters stabilize or the loss function stops decreasing. Code example. Explanation of code. 1. Data generation. We generate synthetic linear data with some noise. 2. Parameter initialization. We initialize the model parameters, theta, randomly. 3. Bias term addition. We add a bias term, column of ones, to the input data, x. 4. Gradient descent loop. We iterate 1000 times, computing the gradient of the loss function and updating the parameters accordingly. 5. Parameter update. The parameters are updated by subtracting the product of the learning rate and the gradients from the current parameters. 6. Output. The final parameters, theta, are printed. Genetic algorithms. Genetic algorithms are optimization techniques inspired by natural selection. They work by evolving a population of candidate solutions over several generations to find the best solution. Detailed explanation. 1. Step 1. Initialize a population of candidate solutions randomly. 2. Step 2. Evaluate the fitness of each candidate solution. 3. Step 3. Select the fittest candidates to form a new generation. 4. Step 4. Apply crossover, recombination, and mutation operators to create new candidate solutions. 5. Step 5. Repeat the process for a specified number of generations or until convergence. Code example. Explanation of code. 1. Fitness function. We define a fitness function that evaluates the fitness of each candidate solution, x squared. 2. Selection. We implement a selection function that selects candidates based on their fitness, with higher fitness candidates having a higher probability of being selected. 3. Crossover. We define a crossover function that recombines two parent solutions to create a new child solution. 4. Mutation. We define a mutation function that randomly mutates a child solution with a specified mutation rate. 5. Population initialization. We initialize a population of 10 candidate solutions randomly. 6. Genetic algorithm loop. We iterate 100 times, selecting the fittest candidates, applying crossover and mutation operators, and forming a new population for each generation. 7. Best solution. The best solution from the final population is printed. Bayesian optimization. Bayesian optimization is a probabilistic model-based optimization technique that is particularly useful for optimizing expensive to evaluate functions. It builds a surrogate model of the objective function and uses it to select the most promising points to evaluate. Detailed explanation. 1. Step 1. Initialize by evaluating the objective function at a few points. 2. Step 2. Fit a surrogate model, e.g., Gaussian process, to the observed data. 3. Step 3. Use the surrogate model to select the next point to evaluate, balancing exploration and exploitation. 4. Step 4. Evaluate the objective function at the selected point and update the surrogate model. 5. Step 5. Repeat the process for a specified number of iterations or until convergence. Code example. Explanation of code. 1. Objective function. We define the objective function we want to minimize, a simple quadratic function. 2. Search space. We define the search space for the optimization, a real-valued interval from 10 to 10. 3. Bayesian optimization. We perform Bayesian optimization using the gp_minimize function from the scop library, specifying the objective function, search space, and number of evaluations, 20. 4. Output. The best score, minimum value of the objective function, and the best parameters, value of x, are printed. 4. Hands-on. Advanced Machine Learning Project. Project Overview. In this project, we will build an advanced machine learning model to predict stock prices using ensemble methods and deploy it on a cloud platform. This project will involve data collection, preprocessing, model building, evaluation, and deployment. Data collection and preprocessing. We will use historical stock price data from Yahoo Finance for this project. The data will be collected, cleaned, and prepared for model training. Code example. Explanation of code. 1. Data collection. We use the Y Finance library to fetch historical stock prices for Apple Inc. AAPL, from January 1, 2020, to January 1, 2023. 2. Data preprocessing. We compute the daily returns using the percentage change of the closing prices and drop any missing values. Model building. We will build an ensemble model using boosting and bagging techniques to predict stock returns. Code example. Explanation of code. 1. Data splitting. We split the data into training and testing sets using train_test_split to evaluate the model's performance on unseen data. 2. Base model initialization. We initialize a decision tree regressor with a maximum depth of 3 as the base model for boosting and bagging. 3. Boosting model initialization and training. We create an ADA boost regressor, specifying the base model, number of estimators, 50, and learning rate, 0.1. 3. The model is then trained on the training data. 4. Bagging model initialization and training. We create a bagging regressor, specifying the base model and number of estimators, 50. 4. The model is then trained on the training data. 5. Making predictions. Predictions are made on the test data using both models. 6. Model evaluation. The mean squared error, MSE, of the predictions from both models is calculated and printed. Model deployment. Finally, we will deploy the trained model on a cloud platform, such as AWS or Google Cloud, to make it accessible for real-time predictions. Code example. Explanation of code. 1. Model saving. We save the trained boosting model to a file using joblib. 2. Model uploading. We upload the model file to an AWS S3 bucket using the Boto3 library, making it accessible for deployment on an AWS service. 5. Anomaly detection. Introduction to anomaly detection. Anomaly detection involves identifying unusual patterns or outliers in data that do not conform to expected behavior. It is widely used in fraud detection, network security, and industrial monitoring. Common techniques. 1. Statistical methods. Identify anomalies based on statistical properties of the data. 2. Machine learning models. Use supervised or unsupervised learning to detect anomalies. Code example. Explanation of code. 1. Model initialization. We initialize an isolation forest model with a contamination rate of 5%, indicating the proportion of anomalies in the data. 2. Model training. The model is trained on the training data. 3. Anomaly prediction. Anomalies in the test data are predicted using the trained model. 4. Identifying anomalous points. The anomalous points in the test data are identified and printed. Conclusion. In this episode, we explored advanced machine learning techniques, including ensemble methods, time series analysis and forecasting, advanced optimization techniques, and anomaly detection. We also completed a hands-on project to predict stock prices using ensemble methods and deployed the model on the cloud. These techniques and projects will enhance your understanding of machine learning and prepare you for more complex applications. Don't forget to like, subscribe, and turn on notifications to stay updated with our latest content. See you in the next episode.